Alright, so now is the time to move on to case 2, which is really the hard case, okay? Now, case 2, why do we have a case 2? Because we were not able to find enough eigenvectors, okay? We have a repeated eigenvalue. When we want to find eigenvectors for a one repeated eigenvalue, you get a one eigenvector, so you don't have enough eigenvectors. Algebraic multiplicity is not equal to geometric multiplicity. So this type of a matrix where you have such eigenvalues and eigenvectors is called a defective matrix, okay? Because you don't have enough eigenvectors. Now what do you do? So let's take an example and understand what do we do here. So let's say we have a n by n matrix, okay? Or let's, for simple case, let's say we have a 2 by 2 matrix, okay? And let's say we have this eigenvalue lambda 1, which is repeated twice. Now to find the eigenvector, what you do is you write a minus lambda 1 I times k1 is equal to 0. You solve this equation. So in the defective case, what you get is you have a repeated eigenvalue, but you only get a one eigenvector, not like case 1. So really now you should have k2, right? How do you find k2? Here's how you find k2. Now closely look what I write, okay? You might have learned this in linear algebra. A minus, we solve another equation. Okay, we need to find k2. Okay, we need to find k2. We solve for capital K2. But our right hand side now is not 0, k1. Okay, so what do we do? We find that capital K2, but using in the right hand side, using the previously find eigenvector, the natural eigenvector you found, you use that to find that other eigenvector K2, linearly independent vector to K1. Now this is a non-natural process. I mean, what I meant by is this is a deviate from what we have been doing previously, right? Previously we were able to find k2 by just using normal equation like this. So this type of eigenvector is called generalized eigenvector. I'm sure you must have learned this in your linear algebra course, okay? So k2 is a generalized eigenvector. So that is how we find all the eigenvectors we need, okay? Alright, so that is not the only difference. Now in case 2, the way we write the general solution is also very different from case 1, and it's also very different from distinct eigenvalue case, okay? Here's how we write the general solution. So let's learn case by case, okay? So let's say case by case means size of the matrix, depends on the size of the matrix. Let's say you have a 2 by 2 matrix and we have a repeated eigenvalue lambda 1. Well, why don't we use the same space? So that is what we did, okay? So we have a 2 by 2 matrix and lambda 1 is the repeated eigenvalue, repeated twice. K1 is the original eigenvector. So let me call it the natural eigenvector, okay? Because we use the most natural way. And K2 is the generalized eigenvector. Now the way you write the solution is you construct the fundamental set of solutions first, okay? Now here's how you do it. So here this is a 2 by 2 system. So how many fundamental set of solutions you need? How many solutions in the fundamental set? 2, right? So namely x1 and x2. Construct x1 by using the natural eigenvector. So that means k1 times e to the lambda 1t. So that's the first solution in the fundamental set of solution. Now you want to create the second linearly independent solution from x1. Now the way you do is yes, use k2 times e to the lambda 1t, okay? But not only this, plus, now this is the important part, plus, okay, you write the previous one, okay, previous solution from the fundamental set of solution. So the previous one means the one that was associated with the same repeated eigenvalue, okay? So this is within the repeated eigenvalues. That is important. So the previous one is, so I have a space here. Let me have a space k1 e to the lambda 1t. So I just took x1, multiplied by t. Okay, so this is how you write the second fundamental solution in the set. But now this is not the general solution. Okay, all right, so this is somewhat similar to section 4.3 case. Okay, we have m1 is the repeated root, twice repeated root. The first solution is e to the m1x, the second one is x e to the m1x. But here it's little bit different because you use the previous one and multiply it by t, not the current one. Okay, not the current one, the previous one you multiplied by t. Now how do you write the general solution? As a linear combination of these two. So general solution is c1 k1 e to the lambda 1t plus c2, the whole thing multiplied by c2. Okay, so see, it's a little bit low. Now we have to analyze this case by case, because when it comes to 3 by 3, it gets a little bit complicated. Okay, so 3 by 3. Let's say we have a 3 by 3 system. Okay, we have a 3 by 3 system with lambda 1 as 3 times repeated. So 3 times repeated eigenvalues. So we get eigenvectors. Let's say k1 is the natural one, k2 is the generalized one, and k3 is also the generalized one. So how to find k3? Now we know how to find k2, but how to find k3 we will see it from an example. But let's say these k2 and k3 are generalized eigenvectors. That means we deviate from our usual method. Remember, right hand side is now not 0. We use the previous eigenvector in the right hand side and find this k2 and k3. Okay, now how do you write the solution? So we have, this is a 3 by 3 system, so we have 3 solutions in the fundamental set. The first solution is x1 k1, the natural one, e to the lambda 1t. Now you know how to write the second one, right? k2 e to the lambda 1t plus t times k1 e to the lambda 1t. Okay, okay, now the third one is k3 e to the lambda 1t, okay, plus kt times k2 e to the lambda 1t. Okay, so it's not that I multiply this whole thing by t. Okay, so it's just I took the second part, second eigenvector. Okay, the previous eigenvector times 2, generalized eigenvector times t e to the lambda 1t. The third part of the solution, the part that is corresponding to k1, is t square over 2 k1 e to the lambda 1t. So that is how you write the third solution. Okay, now you might see this as well, wait a minute. So we write the third part and we can just multiply this second solution by t and get this, right? Yes, we can, but here we will have t square over 2. This over 2 does not come if I just multiply the second part by t. But of course you can multiply the second part by t and just you can add this 2 by yourself later. But or you can understand it, the second part is like k2 e to the lambda 1t times t. Now you go to the k1 times t square over 2 e to the lambda 1t. So that is how we construct the 3 solutions. Now how do we write the general solution? Take the linear combination. Take the linear combination of these x1, x2 and x3. c1 times x1 plus c2 times x2 plus c3 times x3. Okay, so it's a little bit complicated and you have to memorize this. Okay, all right. Next thing is, okay, now what do I do if I have a 3 by 3 system as lambda 1 is the single eigenvalue and lambda 2 is repeated. So lambda 1 is non-repeated. So the first solution is here x1 e to the lambda 1t k1. So that's non-repeated. So leave him be. Leave him be. That's a normal one. So leave him be. x2 is, now you have lambda 2 times repeated, so we will get k2 naturally. Okay, we will get a one eigenvector naturally for sure. Then the generalized one will be k3. Okay, understand that. So we can write the second solution as e to the lambda 2t times k2. Now here we don't multiply by t because that lambda 1 was not a repeated one. It has nothing to do with lambda 2. So that is why I say leave him be. Now this x2 is the first part that is associated with the repeated eigenvalue lambda 2. Now the way you write x3 is, well, t times this x2, right? T times this x2, t e to the lambda 2t k2 plus k3 e to the lambda 2t. So that is how you write the x3. Now you take the linear combination of these three and then you can write the general solution. So there's one more case that I think I didn't discuss, but generally we can write the general solution using this formula. It's this formula explain if you have algebraic multiplicity of m of eigenvalue lambda 1. This formula explain how can we write the general solution. But really what I did here in this video is I think 3 cases. So those are the 3 cases that you usually get. We do not get crazy about getting 4x4 matrices or something like that. I think I covered the cases. So these are the 3 cases that can occur. So yeah, just understand this and remember this. So this is how we write the general solution when we have special case 2. But I'm yet to do an example from special case 2, which I will do in the next video. Okay. All right. Thank you.